think, did I post an answer key for the last test? I did?
Yeah, I think it was like
7 days.
Yeah. The thing is, since it's like sort of a take home, one of the things that you need to do to prepare for the test is to be able to check your answers in different ways, when there's no key available. And so what ways can you check your answer? And so
there's some problems you just can't check the answer.
like which ones in particular?
Let's see. Like, you mean like by looking it up to check your answer, or like check your answer from like reverse engineering or plugging back in?
No, both ways. You can look it up and reverse engineer.
Okay.
Since it is. But no, I could do the key up earlier if you want. The key's helpful. It's just it's an important thing to be able to do when you don't have a particular key. So you look for sample problems similar to it, or the homework or whatnot. Were there any questions about the test? Any particular problems that you're having,
Well, we haven't covered all this stuff yet, right?
I mean, just the stuff that we covered,
Um,
like oxidation states or whatnot. Well, if something comes up, you can always ask me too. It's no problem. We can go through it in class as well. But here's the test. As you can see, you're going to have these chemical reactions here. And one thing is, if you can't get the correct formula, you're going to lose a lot of points. So make sure you review your nomenclature to get the correct formula here. Okay. So I left a bigger gap for exam 2, so you have extra time to do the nomenclature stuff. This one we'll talk. This one we could do in class tomorrow. I was thinking of doing something like that. All right. Well, if something comes up, let me know regarding this. But this one you might recognize. Have you done the chapter 5 homework? If you've done the chapter 5 homework, you'll recognize this particular problem. So anyway, we'll go on. Any other questions? I'm going to continue with chapter 6 here. And then I still owe you a lecture to get a little bit caught up. And so we'll try to finish up chapter 6 today. So this is one of the applications. This is the same thing in Chem 4. You probably recognize this equation from Chem 4 or Intro Chem. And that is the molar mass is equal to the density times R times T divided by P, the pressure. Because M over V is the density. We can also rearrange this equation to solve for the density. If we rearrange that equation and solve it for the density is equal to the molar mass times P divided by RT. And so this is another equation that is in Chem 4. So we could either calculate the density if we know the molar mass at any temperature and pressure. So this is very useful. Or we can calculate the molar mass the molar mass. Usually if you want the molar mass, we could use a mass spectrometer, but we could also use gas. If it's a gas, we could use certain properties of the gas, like the density, the temperature, the pressure, the mass volume, those kinds of things.
MP over RT?
Yeah, molar, M stands for molar mass, this M here. Molar mass times P divided by RT. Okay. So that's the MP over RTs here. They use a different symbol for density. They use the symbol delta here, rather than D, like in Chem 4. And so the delta, or density, is equal to mass over volume. And so there are different ways. We could have derived this alternately. The volume is equal to nRT over P. We could substitute that in here. If we substitute that in here, then this is equal to the mass over nRT over P, which is going to equal the mass times the pressure divided by nRT. And then they do this same thing here. The mass, grams over N, the moles, grams per mole is molar mass. And so they'll just substitute the molar mass, MP over RT. So we can derive these things in different ways, given the ideal gas law. Oh, the density here is in grams per liter, not grams per milliliter. Gases are about 1,000 times less dense. So grams per liter is a more convenient unit to use. Now, gases in stoichiometry, we have different ways of doing it. The easiest way of doing it is by using Avogadro's law. Avogadro's law is also called the law of combining volumes. And that's the easiest route to this. Except you can be thrown off. So for example, if I have H2 gas, I'll need 2 of those plus an O2 gas, 1 of those. And I'm going to get 2 H2O liquids. Normally, water we'll write down as a liquid here. And so in the law of combining volume says this. Let's say I have 2 liters of hydrogen gas. How many liters of oxygen gas would I need? 1 liter. And how many liters of H2O liquid would I form? You'd expect 2 liters, but 2 liters is incorrect. Why? It's not 2 liters. The reason it's not 2 liters is because H2O is not a gas, it's a liquid. And so we can't use Avogadro's law because it's not even a gas. Sometimes it's a gas. If I wrote G here, then yes, 2 liters would be correct. And so if this were 2 H2O gas, then 2 liters would be correct. But since it's H2O liquid, 2 liters is incorrect. We could do a quick calculation in our head. Let's do this at RTP. What does RTP stand for? We'll go with a P, room temperature, and a pressure of 1 atmosphere. So I should say RT 1 atmosphere. Because I'm not going to use standard pressure. What is standard pressure? Standard pressure is 1 bar, which is about 0.9 something atmospheres. So I have it memorized. For example, 1 mole of gas at RT 1 atmosphere is 24.45 liters. So that would be 1 mole of oxygen. So if I take 24.45 liters of O2 and then double it, that would be 48.90. 48.90 liters of H2. Okay, so this would be 2 moles of hydrogen. This would be 1 mole of oxygen. And that's going to produce how many moles of water? This is going to produce 2 moles of H2O. 2 moles of H2O is 36 grams. 36 point, no, H2O is 18.02, so 36.04 grams, which is going to give us 36.04 milliliters, which is going to give us 0.03604 liters. So we form 0.03604 liters of H2O liquid. Or if H2O was a gas, then we just form 48.90 liters. That would be 2 moles of H2O gas. So we have to be careful. The law of combining volumes does not work for solids and liquids. It works for gases. And then there's one other constraint, and that is all the gases have to be at the same temperature and pressure. So if the product gases are at a different temperature and pressure and the reactant gases, then we can use it. We'd have to just use our standard stoichiometry. I don't know why we don't have our standard stoichiometry here. Let me insert. Blank slide. So normally in our stoichiometry map, we'll go from moles of A to moles of B using, the balanced chemical equation to figure out the mole ratio here. So just do a mole to mole conversion. But let's say we have volume of A gas. If we have volume of A gas and we want to go to volume of B gas, then if the temperature and pressure are constant, then we can just do a volume to volume ratio. And that's Avogadro's. If they're different, then we have to do this. If they're different, what I usually do is I use the molar volume. The molar volume is equal to RT over P. So it's a quick calculation here. Do that. And this tells us the liters per mole. And so I just flip it over, 1 over the molar volume and divide by it. Over here, I just calculate the molar volume for the new conditions, which is equal to RT over P. And so these are quick calculations, and then I use these as conversion factors here. This would be in liters per mole. Here. So I'd have to flip this one over. But that's common. So this is stoichiometry here. Now we're going to be looking at mixtures more thoroughly here. We look at different things like mole fraction or percentage. We can go from fraction to percentage by multiplying by 100%, easily. Or we could leave it in fractional form. That's one way of describing a gas mixture, the mole fraction of each component. So I might do moles of A over total moles. That's the fraction. And if I want to convert it to a percentage, then I'll multiply it by 100%. But oftentimes we'll leave it as a fraction. Mole fractions are given this symbol, chi. Is that chi? I don't know. That's not chi, is that? It's given this weird symbol, like an X. That's a mole fraction. We'll look at this symbol more later. But for right now, you don't have to worry about this symbol. We have pressure fraction. Or percentage. This is called Dalton's mixture. And there's Dalton's law. And then we have volume fraction or percentage. This is called Avogadro's. mixture. For a given mixture, this is one of the key things here. The mole fraction, let's say moles of 8 over total moles, is equal to the pressure fraction, that is the partial pressure of A over the total pressure, which is equal to the volume fraction, VA over V total. They're numerically equal, but these cannot be simultaneously true. It's one or the other. Is true. Whereas the mole fraction is always true, regardless. And so we're going to be using Dalton's law and Avogadro's law to, and the mole fraction to investigate gas mixtures. Dalton's law is fairly simple. That is, the total pressure is if you add the individual pressures. So let's say you had gas A and gas B, and then total pressure would be the pressure exerted by the A particles hitting the wall and the B particles hitting the wall. So we can see that, visually, something like this. If I have gas A is these black ones, they're going to exert a pressure by striking the walls of the container, and that generates a force, per unit area. And it's going to depend on how many of these black particles we have in there. Let's say the B were these blue ones. And so the total pressure will be the sum of the pressure generated by the black ones plus the pressure generated by the blue ones. That's Dalton's law. The volume that each gas would individually occupy at a pressure equal to P total is this. This is kind of weird, because they're mixing out Dalton's and Avogadro's. And so we'll talk about Avogadro's separately. I'm going to skip all that. So here's the mole fraction, which is equal to pressure fraction, which is equal to volume fraction. And this symbol's usually reserved for the mole fraction. And so if we want the partial pressure of A, then we'll just take the fraction of the total pressure that belongs to A. And so let's say half the gas is A, then it'll be 1/2 the total pressure. The same thing with the volume fraction. If I want the volume fraction of A, then I'll just take the mole fraction. Let's say half the gas is A, then half the total volume is A. However, these two cannot be true simultaneously. It's one or the other. And so there's some more ways. I like to think about this visually rather than mathematically, which we can. Let's take this gas and look at it visually versus mathematically. When we do Dalton's law, the volume of the gases has to be the same. And so we call that constant volume.
So is it like to use the law of combining volumes, we have the same temperature, pressure, and
Yeah, the law, Avogadro's law, the law of combining volumes, it has to be the same pressure and temperature. But it's probably easier to see visually. Okay, so if I have 5.0 liters of gas A plus 5.0 liters of gas B, that's going to equal how many liters of mixture? No, 5.0 liters of A and B mixture. The reason is it has to be done under constant volume. That means all the volumes are the same. So if you take 10 liters of oxygen and 10 liters of nitrogen, how many liters of oxygen-nitrogen mixture do you end up with? 10 liters. All the volumes are the same.
What law is this?
Dalton's law. It's called Dalton's law. Dalton's law is a way of visualizing mixtures. So if I have a mixture like this, I can divide it into the components of the mixture. The components of the mixture would be 10 liters of the blue and 10 liters of the red. Starting, not 10 liters, 5 liters. And we're dealing with 5 liters here.
How come that's true?
Hmm?
How come that's true?
I'm sorry, can you
How
repeat?
come that's true, like with constant volume? Like if we add both of these gases together, why is it 5 liters not 5?
It's just a way of it's just one way of visualizing the mixture. We can get the mole fraction and we can figure out what the pressure fraction is. So in this case here, we start off with 2.4 atmospheres. This is hydrogen plus 6 atmospheres of helium. And so when we combine these two, what's the total pressure going to be? 8.4 atmospheres, because now we have the blue ones striking the wall. The blue one striking the wall is 2.4 atmospheres, but in addition to the blue ones, we have the red one striking the wall. The red one striking the wall is 6 atmospheres worth. And so altogether, we're going to have 8.4 atmospheres worth of collisions here in this big container. Or not the big container, it's the same size container, right? And so this is one way of visualizing it. We can also determine the volume fraction. So when we do volume fraction, you know, what volume of hydrogen and what volume of helium do we have here? Well, what volume we have depends on if you're talking about Daltons or if you're talking Avogadros. And so there's another way of separating this. The other way of separating this is by Avogadros. So we'll take a look at Avogadros next. So do that. This is Dalton's. So this is 5 liters. So what I'm going to do is I'm going to calculate the mole fraction of these. Let's see, what was the mole fraction of, or I could calculate the pressure fraction, because the mole fraction and the pressure fraction are the same. So let's go ahead and calculate the pressure fraction of hydrogen. And the pressure fraction of hydrogen is going to be 2.4 atmospheres worth of hydrogen over 8.4 atmospheres total. So that's 2.4 out of 8.4 total. That's a pressure fraction. So let's go ahead and I'm going to punch that in my calculator. .4 divided by 8.4, and that's gives me a pressure fraction of 0.2857 in decimal form. 0.2857 over 1. I'm only allowed 2 sig figs. I'm carrying extra, which is going to give me a percentage of 28.57% hydrogen. All right, let's go ahead and calculate the pressure fraction of helium. Helium is 6.0 over 8.4 total atmospheres, which is 6. Well, it's going to be the rest, the balance. The balance of this, I'll just do it in my head. It should come out to 61.43%, or 0.6143 over 1. And so if I want to divide this in Avogadros, then the pressure fraction is equal to the mole fraction, which is equal to the volume fraction. Or the pressure percentage is equal to the volume percentage, which is equal to the mole percentage. And so how much hydrogen do I have? Well, I could just do this. I could just take the, I could use any of these here, but I'll just go ahead and use the original mole fraction. 2.4 out of 8.4 parts of 5.0 liters gives us how many liters? And so I'll just do 0.2857 times. Oops. This is a new calculator. 0.2857 times 5. 1.428 liters of hydrogen. And then we look at the mole fraction or pressure fraction of helium. So I'm going to do 0.6145. I'm sorry? 7.1? Oh, did I screw it up? Okay. Tell me again, the hydrogen?
The helium, 71%.
Oh, 71%? Oh, okay, yeah, sorry. You're right, 71% here. 0.7143. I'll just do it in decimal form, times 5. 3.5715 liters. And so what this means is that I have 1.428 liters, or let's just go 1.4. I have 1.4 liters of hydrogen plus 3.6 liters of helium. And that's going to give us a total of how many liters? 5 liters of mixture. So what we have to do is we have to be in two, we can be in 3 different, we can be in like 3 different kind of dimensions. The mole fraction works everywhere, but we have to either stick in the Dalton's dimension, so we think in terms of Dalton. Now, if you think in terms of Dalton, then we visualize mixtures differently. or we switch over to Avogadros. And if we look at a mixture in terms of Avogadros, we think about the mixture totally differently. But you know what? They're all the same. They all kind of give us the same. So over here, I had 5 liters of hydrogen and 5 liters of helium. But here I have 1.4 liters of hydrogen and 3.6 liters of helium. And so why the difference there? So can somebody tell me why? Because when we do Avogadros, we have to do it under constant pressure. Let's take a look at this mixture. If I take this mixture and go backwards, I take this mixture and I remove out all the hydrogen. The total pressure has gone down because now I don't have all the red heliums. And so the pressure has gone way down. You see that? And then if I take just the red ones and remove those over into this container, then the pressure's gone down again. And so the pressures in Dalton's, the pressures are additive. And so this is the very famous equation in Dalton's law. The very famous equation in Dalton's law is this. This is Dalton's law of partial pressures, that the total pressure is equal to PA plus PB plus et cetera. The individual pressures, we can calculate that. So for example, PA is equal to the mole fraction, that is NA over N total, times P total, etc. PB is equal to the mole fraction of B, etc. And so the pressures are additive. The volumes are constant. VA is equal to VB, which is equal to V total. And so again, that's what we mean by constant volume. Sorry, I'm going to flip back down to here. Over here in Avogadros, the volumes are what is this? This is not Avogadros, sorry. This is Avogadros here. Over here, the volumes are additive. So VA, how did they write this one here? Let me just see real quick. Oh, here. Or here, we'll just do it here. V total is equal to VA plus VB, etc. And if I want VA, then, well, here it is. VA is equal to the mole fraction of A over V total. And so that's what we got here. So here, 1.4 plus 3.6 gives us 5.0 liters here. Now the pressures are added, so the pressure of the hydrogen plus the pressure of the helium is equal to what? P total. It's not equal to P total. That is, the pressures are not additive. The pressure of the hydrogen is equal to the pressure of the helium, which is equal to P total. So what we're doing here is this. We have to make the container smaller because there are fewer molecules here. We make the container smaller so it generates exactly the same pressure. And so this is 8.4 atmospheres. And so I'm going to have 8.4 atmospheres of hydrogen. And then I make this container smaller for the helium. Helium's monatomic. And so I'll have 8.4 atmospheres of helium. So normally, under Dalton's, we take 8.4 atmospheres of hydrogen plus 8.4 atmospheres of helium, and we get 16.8 atmospheres of mixture. But that's only for Dalton's. We've switched our dimension to Avogadro's now. With Avogadro's, what we're going to do is we're just going to add the two containers without squeezing the gas further or expanding the gas. And so when we add these two containers together, we're going to get exactly the same pressure as we had before. So we're going to get 8.4 atmospheres of mixture.
So do you prefer that we know one or the other?
You have to know both.
We're gonna test on both?
You have to know both. And you have to be flexible enough to switch from one to the other. It's not one or the other. Unfortunately, well, in Chem 4, it's Dalton's. They only talked about Dalton's. I threw in Avogadro's in there. But,
So just to make sure, for Dalton's, it's under constant volume, and Avogadro's is under constant pressure.
yeah. So the question was, Dalton is constant volume, and Avogadro's is constant pressure. Let's take 1 liter of air at 1 atmosphere. And what does air consist primarily of? Nitrogen and oxygen. What do we have more of, nitrogen or oxygen? Nitrogen. So nitrogen I'm going to do in blue, oxygen I'm going to do in red. Do you know the mole fraction or the percentages? It's a percentage. Yeah, it's like 21, is it 21% oxygen? Yeah. So it's about, you know what, I'm going to just round it down. Let's make it easy. The number's easy. I'm going to make it about 20% oxygen and about how much percent nitrogen? About, well, 78, but because there's other stuff, but I'm going to make it add up to 100%. And so this is not really air. Let me put that in quotation mark. Or I'll just say about 20%. It's about 20, you're right, it's 21% oxygen, 78% nitrogen, and about 1% other stuff. Something around there. So let's imagine this mixture as being Dalton's. Let's separate it. If this were Dalton's, how many liters of oxygen do I have? If this were Dalton's, how many liters of oxygen do I have? I have 1 liter of oxygen. And then how many liters of nitrogen do I have? Yeah, also 1 liter of nitrogen. And so if I take 1 liter of oxygen plus 1 liter of nitrogen, how many liters of air do I form? 1 liter. And so the volumes are not added in. But if I take just the oxygen out, then there's no, actually I should just copy and paste that. There's no helium. I'm not helium. I'm thinking of the last problem. There's no, this is not oxygen either. This is nitrogen, sorry. Oxygen should be the red. if I remove all the oxygen out of there, what's going to happen to the pressure? The pressure is going to go way down because you don't have the blue molecules colliding. So what do you think the pressure is going to be? I picked the mole fraction or the mole percentage easy to make it easier to calculate the pressure. What's the pressure going to be? How many atmospheres of oxygen will I have? 0.2 atmospheres is correct. So I'm going to get 0.2 atmospheres of oxygen. The pressure is going to go way down. And the nitrogen is no longer going to be at 1 atmosphere as the mixture was. What's the nitrogen going to be at now? 0.8 atmospheres. Okay, if we are in the Dalton's dimension, then it does not overlap with Avogadro's. It cannot be both Avogadro's and Dalton's at the same time. If we do Avogadro's, how many liters of oxygen do I have? I'll tell you. 0.2. We have to cut the volume by 80% in order to get the same pressure. And so we're going to have 0.2 liters of oxygen, but the pressure of the oxygen will be 1 atmosphere. And then how many liters of nitrogen will we have? 0.8 liters. But the pressure of the nitrogen will be 1 atmosphere. Oops, the wrong color. So we're just going to compress it so it makes 1 atmosphere. So the mole fraction of nitrogen and the mole fraction of oxygen is always the same. So that's like 20 out of 100. This is going to be, whoops, this is 80 out of 100. This is 20 out of 100. And so mole fraction, mole percent is always true. Dalton's is true if the volume is constant. Avogadro's is true if the pressure is constant. So 1 atmosphere of oxygen plus 1 atmosphere of oxygen, 1 atmosphere of oxygen plus 1 atmosphere of nitrogen equals how many atmospheres of mixture in Avogadro's? 1 atmosphere.
And moles are just added for either?
Moles is always true, doesn't matter. Moles is always true. And so Dalton's, again, is constant volume, and Avogadro's is constant pressure. I'm sorry? Okay, yeah, that would be helpful. No. What they have in common is they'll give you the same numbers in the ideal gas law. That's what they'll have in common. And so P or V or something, actually N will be always the same. Actually, we could make a little diagram if you want. I'll show you what it looks like. And the temperature's got to be constant, but if the pressure goes up, the volume goes down, right? Or if the volume goes up, the pressure goes down. So there's a relationship between pressure and volume here. And so the number of moles is fixed. So it depends on how we want to do this. For Dalton's, the pressure is variable. For Avogadro's, the volume is variable. And then we end up with the same moles in the end. So your Venn diagram would have N in the middle. And pressure on one side, the volume on the other. Let's look at an application of this. When we collect gases over water, what happens is the gas gets saturated with water vapor, and it becomes 100% humid. And so if you were stuck inside this container here, you'd be subject to 100% humidity because there'd be a lot of water vapor in here, in addition to the gas. And so we'll have the gas come in here this way. And as it bubbles through water here, it becomes saturated with water vapor. And when it's saturated, we call it 100% humid. 100% humidity. This is like an indoor swimming pool. El Camino has an indoor swimming pool. You go in there and it's really humid, isn't it? It's really humid because the air in there has been saturated with water vapor, so the humidity is quite high. It doesn't matter how big, you know, if we make the volume of the gas bigger, then more water will evaporate. This is called a dynamic equilibrium here. And in this dynamic equilibrium, we're going to have evaporation and condensation occur. So if we make the volume bigger, then more evaporation will occur to saturate it, you know. Or if we make it smaller, then some condensation will occur to keep it at 100% saturated. We don't want it super saturated. So how much water, humidity depends on temperature. How much water is evaporated, this depends on temperature. So this is like a barometer, except this barometer doesn't have a vacuum here. This barometer has some gas here. So which weighs more, the gas or the atmosphere? The atmosphere is pushing on the surface outside here, and the gas is pushing on the surface inside here. So this is like an offset balance. Which is heavier, the atmosphere or the gas? The atmosphere is heavier because it's pushing this side up. And so this is like a seesaw. The atmosphere is here. The water levels should be level like this. But the atmosphere is pushing here, and that pushes the water level up on the inside. Can you see that?
It was like the other.
And so if the gas were heavier, then it pushed this down and pushed this up. Do you see that? So right now, the pressure of the gas weighs less than the atmosphere because inside here, you have the gas pushing down. And then outside here, you have the atmosphere pushing down. And the atmosphere has got to be heavier to create these unequal levels here. And so we can do this like we did with the manometer. Do you remember the manometer? What we do is we set the level equal, like this. And therefore, from the manometer, we get P of the atmosphere is equal to the pressure of the gas, the weight of the gas, plus the weight of the water. We're not using mercury here. We're using water. And so the weight of the water will be measured by the height of the water in millimeters. of water. So the weight of the water is measured by the height of the water in millimeters. And so what we call it millimeters of H2O liquid. And then what we can do is we can convert this into millimeters of Hg liquid. How we do that is we take advantage of the density. The density of water is about 1. The density of mercury is like 13. Let me get the density of mercury to more sig figs. I don't have it memorized. .6 will go. So if I have this much water, I'd need 13, actually, let me do this the other way. If I had this much mercury, mercury is very heavy, right? And I want the equivalent weight in water, I'd need 13.6 times more water. 13.6 times more water. And so the conversion here is that for every millimeter of mercury, 1 millimeter of mercury, I need 13.6 millimeters of water because mercury weighs 13.6 times that. Does that make sense, this conversion factor here? And so I can measure how many millimeters of water I have and then convert that into millimeters of mercury by using this conversion factor here. But you know, that's kind of a pain because that means you have to get a ruler here, you know, and then measure how many millimeters of water. And it's not easy because you have to put your head, well, if you have a tub like this, it's okay, but we do this in the sink. And so it's not easy to do at all. And so we don't even bother doing this. You know what we do? We do something called equalizing the pressures. Alternatively, we can equalize the pressures like this. So the gas is at a lower pressure. It weighs less. So what we're going to do is we're going to force this down. As we force this down, it's going to try to push the liquid in here further. Although this is wrong. This drawing, this sketch is totally wrong. Because what's going to happen is it's going to force more water in here. It's going to force more water in here, compressing the gas. So the water level should be way up here. It compresses the gas and it squeezes the gas so that the pressure of the gas eventually becomes equal to the pressure of the atmosphere. And so what we're doing is we're forcing more water in there to increase the pressure of the gas so that the two levels are equal. And so this is not consecutive sketches here. This is just an alternate one. So if the two levels are equal, what that means is that the pressure of the gas and the barometric pressure or the atmospheric pressure are exactly the same. And so that's easier. Let's say the liquid level were under here. If it were under here, we'd lift this up, sucking the water out, you know? Because if the liquid level inside here is down here, the gas weighs more than the barometric. So if we lift this up, it sucks the water out, creating a vacuum here. And eventually what we can do is we can get the two levels equal. When we get the two levels equal, then the pressure of the gas in here is equal to the barometric pressure out here. But the situation is this is not pure gas. What is this? This is a gas mixture because our gas has been contaminated with what? Our water vapor. Our gas has been contaminated with water vapor. Let's say it's a brown gas, and now I've got water vapor. And so what we do here is this. We need to figure out either Dalton's, we need to either treat this as Dalton's or Avogadro's. And so that's the first thing. We got to, do we want to treat this as a Dalton's or do we want to treat this as an Avogadro's? Yeah, we're going to treat this as a Dalton's mixture. So what we're going to do is we're going to get the, actually, with this, maybe I shouldn't talk too much about this.
Do you have a word problem involving this?
We're going to do a lab involving this. In fact, I'm going to talk, let me do this. We're going to do a lab. The first calculation in the lab, we have to use Dalton's. The second calculation, or no, the first calculation in the lab, we use Avogadro's. The second calculation in the lab, we use Dalton's. And that's word problems. And actually, that's a lab we're actually going to do. So if we treat this as a Dalton's mixture, then what we have here is the vapor pressure of the water. And so the total pressure of the gas is equal to the pressure of the gas plus the pressure of the water vapor. The pressure of the water vapor is constant for a given temperature. So these are all 100% relative humidity. So at 25 degrees C, the 100% relative humidity means we have 23.78 millimeters of mercury of water vapor. That's what. And 100%, it's called relative humidity because it changes depending on the temperature. And so at hotter temperatures, it's more humid. At colder temperatures, it's less humid, and that's still 100%. You know. The more that you increase the heat, the more evaporation you're going to get, and the higher the humidity. But 100% is defined for a given temperature, so these are all 100% humid. It's just you can't force more water. At 25 degrees, you can't get more water vapor than this. It's saturated. It's maxed out. And so we treat it as a Dalton. So the volume we can measure, the pressure we can measure, and then the water vapor here, we can determine the pressure of the water vapor based on the temperature, and then we can figure out what the pressure of the gas is. The pressure of the pure gas is just the total pressure minus the pressure of the water vapor. We're going to do this in a lab. So I'll wait I'll wait and talk about this more later. The lab is also going to involve Avogadro, so we'll talk about that too. And so I'm going to skip this temporarily for now, and then we're going to go to kinetic molecular theory. Kinetic molecular theory, you just treat gases as mostly empty space in which these particles move randomly, colliding with the walls. This is kinetic molecular theory of ideal gases. The particles are point masses in constant random straight line motion. Have you ever heard the word point mass? In physics, they use this to indicate, there's a single point. And we can treat this mass, the mass of the atom, as just being concentrated in a single point here. And so what that does is it collapses the volume and the shapes of these things, so we don't treat them as particles. So an ideal gas wouldn't have atoms like this. An ideal gas would have points like this. And do you know what the volume of the point is? The volume of the point is 0. So what we do is we collapse that atom and make it a hypothetical 0 volume point. But we don't have to worry about that. Don't worry about it so much. Molecules are separated by great distances. Well, these aren't molecules here. These are atoms here. But we could have molecules too. Molecules would be the same thing. They collapse into a point mass. They collide only fleetingly, and most of the time they are not colliding. Most of the time they're going through space. This is ideal. And so this is ideal here. Point masses equals 0 volume.
Professor,
Mhm.
so we have to remember the point volume or not? That's equal 0.
You don't have to remember the word point mass. All you have to know is that ideal gases assume that the particles have 0 volume. So if I have 1 liter of gas, in an ideal gas, 1 liter of gas is equal to 1 liter of empty space. In a real gas, 1 liter of gas equals X liters of empty space plus Y liters of particle volume, particles being atoms or molecules. And so in a real gas, I'd have slightly less than 1 liter of empty space. In an ideal gas, I'd have 1 liter because we treat all the particles as point volumes, which means they have no volume. Or point masses, sorry. In an ideal gas, we assume that there are no forces of repulsion or attraction. Usually there's forces of attraction. And so we assume that there are no IMFs, no intermolecular forces. IMFs are intermolecular forces. In a real gas, IMFs exist. Which results in sticky molecules. So in an ideal gas, the particles just bounce off one another. In a real gas, sometimes they get stuck or stick. It's like if you have billiard balls, you know, pool balls. If you have pool balls, they just bounce off each other quite nicely. But if you have like soft clay balls, you know, that are wet, you know, when you throw them at each other, are they going to bounce off so nicely? No, sometimes they get stuck together. And so real gases can get stuck together. If the molecules or the particles are sticky, then that's going to alter the pressure, you know, because they don't bounce off as forcefully. Individual molecules may gain or lose energy, but the total energy remains constant. And so this is kinetic molecular theory, and then there's physics, you know, laws of motion, that kind of thing. So in a real gas, we have 3 types of motion. Do you know the 3 types of motion in a real gas? We have something called translational motion, which goes from one point in space to another point in space. That's translational. But we also have other ones if it's a molecule. If it's a molecule, we could also have rotational. So if these are water molecules, they'd be rotating in space. And then we have one more type of motion. Do you know what one more type of motion is? Vibrational motion. And so, you know, people try to model these real gases more accurately. For an ideal gas, we only have one type of motion. What is that motion? Translational motion only. So that makes the physics a lot easier for real gases, because for real gases, if we only have translational motion, then there's only one energy dealing with that, you know, which is, have you heard of 1/2 mv squared? 1/2 mv squared is the energy, kinetic energy, for an ideal gas. But anyway, let's let me look up. This is trying to model it. This is probably H2O liquid. And so we have translational motion, we have rotational motion, and we have vibrational motion. I don't know if they did the modeling with vibrational. They might have left out, it looks like they left out the vibrational motion. This is just a calculation. And so if they didn't do the vibrational, it makes things a little less computer intensive. Is this, yeah, this is water. And so you can see that they're kind of sticky. These purple things are when the waters are kind of attracted to one another, and so they're sticking together. Those are hydrogen bonding interactions primarily. Let's see if they're going to freeze this. No, this one's not that interesting.
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application.
And this is ice. Ice at the top, there's no transition motion. If you slow these water molecules down, then they can stick to one another. And ice forms a nice orderly crystalline structure. So the structure of ice is very open. It's an open network like this. It has these gaps here. That's a simulation of water turning into ice. Let's see this one. This is ice melting, so they're just looking at a portion of the ice crystal, showing the well-ordered arrangement. We have crystalline and we have amorphous. Amorphous are going to have less order like the liquid. The liquid state was more amorphous than the solid state here. The solid state is quite nicely ordered. And we can build this ice crystal by just layering on top of these. So we just add more layers to it. This would be the ice crystal here. Ice crystal will have vibrational motion, no rotational, no translational. And so the water molecules are stuck in position. At 0 Kelvin, there's no vibrational either. So if we cool this down to 0 Kelvin. And then, let's see. And so they're just adding more layers. Okay, now you can see the vibrational motion. Eventually, you increase the temperature, that increases the kinetic energy, and then you can start seeing the structure is collapsing. And we're going to melt it. It collapses catastrophically. So once you hit 0 degrees C, the whole thing collapses and converts into liquid water. And so it's very sudden. But this has been slowed down, quite a lot. But it would happen. It's probably a million microseconds here. Or, if you have a big ice cube, it depends on how big the ice cube is. It takes time for the heat to diffuse into this structure here. All right, let me fast forward. Okay, we don't have this completely melting, unfortunately. And then we can also vaporize these. Okay, this is measuring diffusion. So it's something like this. Let's go back to what we were talking about here. So this is kinetic molecular theory. We try to visualize these things as happening. It turns out when you look at like an ice crystal, every single water molecule, are they clones of one another? Exact clones? Are they doing exactly the same dance? Or are they individuals? They're individuals. And the other thing is, do they have exactly the same energy? No, they don't. Even in the liquid phase, if you look at the water, the temperature is at 25 degrees C, but what we see is a distribution of energies. So some of the water molecules are moving faster, some are slower. They're not all the same, even though they're all exactly this. I mean, they're all water molecules. And so what we have here is what's called Maxwell-Boltzmann, or thermal distribution. And all this says is if we have a given temperature, then some molecules are moving slow and some molecules are moving fast. But the bulk of the molecules will be moving around here. The bulk of molecules, now if we look at an ideal gas, the ideal gas only has translational motion. So we're only looking at something called the velocity. 1/2 mv squared. V is for the velocity, m is for the mass. And so the kinetic energy only depends on the velocity, which is the speed of the molecules. And so we have something here. If we look at the whole distribution, and then what we do is we say, okay, I'm going to take that whole distribution and then average it out. That is, I'm going to make all the water molecules move at the same speed. If you make all the water molecules moving at the same speed, then what do you have? You would think you'd have the average speed, right? But it's not the average speed. It's called the root mean square speed. So if I took this whole population and gave it all the same speed, it would have to adopt the root mean squared. The root mean squared is you take the mean, square it, and then you take the square root of it. And so doesn't that just give you the mean? But no, what it is it's kind of an offset. And so the URMS is the effective speed of the whole population. So if you take this whole population and give it one effective speed, then all the molecules would have URMS. This is the median here. No, this is the mean, this is the average. And so you can see it's offset. It's not at the peak here because of this. This is called a high energy tail here. And so it's not a symmetric distribution. This is not a bell-shaped curve. It's a Maxwell-Boltzmann type shaped curve. And the RMS is going to be offset to the shoulder here. And so URMS is the effective speed of the population, and the entire population, I should say. It's you take the mean and you square it, and then take the square root of entire population. Mm-hmm. What, URMS? Yeah, URMS is going to be on the exam. What we want is this. Oh, let me tell you what's going to be on the exam. This is going to be on the exam. This is the physics of this motion. This is the mean, this is the average. These aren't going to be on the test. This one's an important one. Mm-hmm.
So when you say like the mean, you mean like if I was to calculate the mean of like 3, 7, and 10, we would like square 3, square 7, square 10, add them together and square that? Or would we add them together, square it?
Add them together, square. Add them together, divide by 3, square that, and then take the square root. It should come out the same. But the situation here is, well, actually that doesn't quite make sense, right? And so, Right, right. It would be, you would square because you would have negative potentially velocities, and so you would square those to get rid of the negative.
That's without
Um, yeah, or you could take the absolute values, but it's weird. I'll give you off the top of my head. I remember, but I don't remember.
Sorry, can you explain what URMS is?
Well, URMS is if you give the population, it's like, the voltage, probably this might be the easier way of thinking about it. Do you know what the voltage is out of your outlet?
what is that,
110 volts, 110, 115 volts?
Yeah.
Let's just do 110 volts. Do that. And so you have 110 volts coming out, but it's not 110 volts. This is the RMS voltage. That's because we have AC current alternating current. And so when we look at the AC current, the voltage goes up, the voltage goes down, like this. And so we could get some like peak voltages of this. The voltage actually is going to vary from about 120 plus volts down to, let's say, 100 roughly volts. And so it's fluctuating there. And so one way of thinking about it is, okay, if we do this, well, this does look like it. It's actually slightly off because of the way the voltage signal is. This looks like the average, but it's slightly above that. And so this should be less than 100 volts here. But the effective voltage coming from this would be 110 volts. Does that make sense? Maybe not so much, but
Is it like from uncertainty?
no, it's not uncertainty. It's just how this population, one way of thinking about this is just how the population is. And so the voltage, the peak voltage is going to be higher. The peak voltage is about 120. But you can't go off the peak voltage. And so, let me see if I could have I should have a better explanation of this. But let's take a look at this here. So this is just measuring Maxwell-Boltzmann distribution, and so they have these rotating disks where they can segregate it based on speed. And so they can measure the population based on how fast the molecules are moving here. And then we see that. We get a distribution like this. And then from this distribution, if you wanted to assign the molecules just one speed, that is, have the entire population have the exact same speed, what would that speed be? That speed would be the RMS speed. But the RMS speed is kind of weird because it's not the average speed. It's just slightly above the average speed. And so let me try to think of a better analogy for this. But it's over here. This would be the RMS speed. And the RMS speed, we should be able to calculate that because this equation here, which is the square root of 3RT divided by the molar mass here. R is just the gas constant, 8.3145 joules per mole Kelvin. T is just the Kelvin temperature. And then M is the molar mass. And so that would be it there. And then what happens to the distribution at different temperatures? We should know that. So this is hydrogen at 273. If we increase or decrease the temperature, it changes the distribution. So this is oxygen at 273. Oxygen weighs more than hydrogen. And so the molar mass here is 32. Except the molar mass, we have to do it in certain units. So if we do this calculation here, R is going to be joules per mole Kelvin, T is in Kelvin, and the molar mass should be in what units? So the units that we're going to have here are joules per mole Kelvin times Kelvin divided by the molar mass. The molar mass typically is in grams per mole, but we have to change the units here. And therefore, we have to know what the joule is defined as. Do you know what the joule is defined as? 1 joule is equal to 1 kilogram meter squared per second squared. And so the molar mass we have to convert from grams per mole to kilograms per mole. And then that should give it to us. And so what we do here is we do this. If we want to calculate the RMS speed of oxygen, we could do that. U RMS is equal to square root of 3RT over M. And so that's going to be 3 times 8.3145 joules per mole Kelvin times 273 Kelvin divided by the molar mass, which is 32 grams per mole. Actually, we could go 32.00 grams per mole here. And now to get the units to work out, we'll have to convert joules into kilograms meter squared per second squared. And then we're going to have to convert grams into kilograms. So we'll just do that. 1 kilogram is 1,000 grams. And then the units should work out. Because the moles should cancel, the grams cancel, the kilograms cancel, and the Kelvin cancels. And that leaves us with meters squared per second squared. And then we take the square root of that, and we'll get meters per second. So let's go ahead and calculate this here. This is going to be 3 times 8.3145 times 273 divided by 30.032. And then take the square root of that. And this comes out to a URMS of 461.3 meters per second. 461.3 meters per second, we're going to convert that into miles per hour. And so to convert from meters to miles, I'm going to multiply this by there are how many centimeters in a meter? 100 centimeters in a meter. And then there are, in 1 inch, 2.54 centimeters. And then there are, in 1 foot, 12 inches. And then in 1 mile, there's 5,280 feet. And then I'm going to convert seconds into hours. So 60 seconds per minute and 60 minutes per hour. And so let's go ahead and do that times 100 divided by 2.54 divided by 12 divided by 5280 times 60 times 60. So this comes out to 1,031.9 miles per hour. So this is at 273. I wish they had this at 275. They're doing this at STP. And so at 275, the RMS speed would be faster. But the oxygen molecules in this room, some are moving slow, some are moving fast. But if you take that whole population of oxygen molecules in this room and give it one speed, that one speed would be 1,000 miles per hour. Now, helium's moving way faster. Helium's moving way faster because it's much lighter. In fact, helium is how much lighter? So 32 divided by 8 times lighter? No, 4 times lighter. Helium's 4 times lighter. And so if we take the square root of 4, that's 2. And so helium's moving like twice as fast, 2,000 miles an hour. The RMS speed.
Sorry, what did you get for the initial RMS, 461.3?
From this equation here, that's what I got. This is from kinetic molecular theory, this equation is. We didn't go into the derivation of this. But this is the way we calculate the root mean square speed. You have to know how to do this calculation. It's not difficult. I mean,
The 8.3145 is just part, it's
8.3145 is just the gas constant, R. That's it.
So, how come we're not being killed by oxygen gas?
Because the energy, the kinetic energy is equal to 1/2 mv squared, and the mass is so light. So the energy is very small. I don't know, some people might be killed by the oxygen because it's 15 pounds. Like, you know, oxygen is 20%, so 20% about 15 pounds. That's how much oxygen. So it could kill you. It's like if you grew up in a vacuum and then you were exposed to this, you'd be under a lot of pressure.